Hello, everybody. I'm Andrei, and I work for JetBrains as a Senior Vice President of Investments, Research, and Education. Welcome to Regionals. Great things happen when great minds come together. JetBrains wants to seek out great minds all across the globe, support their initiatives, and work together to create great things that will make the world a better place. That's why JetBrains is proud to be a Global Tools sponsor of the ICPC. There are already many great minds working at JetBrains, and together we have created some amazing things, like the Kotlin programming language, for example. It keeps on growing and growing in popularity. In 2017, Google began officially supporting Kotlin as a language for writing Android applications. We have also created professional development tools like Cline for C++ programmers, IntelliJ IDEA for Java, PyCharm for Python, and also educational tools that help people learn and teach programming. The regionals are the biggest contest in the ICPC calendar. Thousands of talented people all over the world team up to solve complex real-world challenges. These contests are the proving ground for future champions. But even if you don't make it through to the finals, the experience of competing in the regionals and the new friends you'll make along the way are priceless. Enjoy the ride. Best of luck to everyone.
Innovation is a journey of doubt and uncertainty. From 5G deployment and its ecosystem came digital transformation in all industries. From Huawei Cloud came the wonders of widespread remote healthcare. From AI machine learning came better, more intelligent ways to protect the Earth. From AI computing came advanced astronomy research and a deeper understanding of the cosmos. From new ways to live, a greener Earth, and futures beyond our imagination. Our journey of innovation will never end.
There are parts of our world where light can't reach. Divides that are too wide for rivers to flow. But technology has the power to help. In remote areas of Nigeria, connectivity brings new life to local communities, opening doors to trade, banking, better education, and healthcare. In Bangladesh, digital training has given more than 240,000 women new opportunities in life. With AI, deaf children everywhere can translate written words into sign language. So no child misses out on the joy of storytelling. In Central America, upcycled smartphones help rangers detect poachers and loggers, keeping rainforests safe for everyone. Our planet may not be perfect, but digital technology can help make it better. In the next 5 years, we want to work together with our partners to help 500 million more people directly benefit from digital technology. Focusing on healthcare, education, environmental protection, and economic equality. Tech for all. Pass it on.
Good evening to all the participants who are here. We just completed the world's largest regional contest, the preliminary round of ICPC 2020. And one objective of having this contest now was especially to create a kind of positive vibe across the contestants community, the student community, where even during this pandemic time, we are all able to come together. We faced a lot of issues while choosing the dates, there were a lot of confusions among the sites whether which site will have the contest or which site will not have the contest. And the discussions went for a long time, maybe for 3 or 4 months. And finally, we decided to go ahead with the dates we had announced. And Amrita is the only site having this kind of a participation. And I know that there was some confusion regarding 2 sites, etc. But now I think there is only one more site that is active now. It's Gwalior site. So I am very fortunate here that the world finalist, one of our old world finalists, that is Balaji, to host this contest in Bala's platform. And I was so peculiar that I wanted to have this contest in his platform. I was so confident that we can do that, because I know there are a lot of contest platforms, but an ICPC contest hosted by a platform developed by the world finalist himself makes a lot of sense. It matters a lot for the ICPC community. And we conducted, in fact, they conducted, Deepa and Bala conducted a lot of practice sessions to make sure that the things are well. And the load during the contest was just seamless. There was no issue at all. And I was wondering why we never thought this idea before, because I know that there are a lot of contest platforms and we have been experimenting with a lot of contest platforms like Dome Judge or Code Chef or Code Forces. But still I wanted to have this one for this year. And let me first congratulate Bala and his team, I mean Bala and his wife, for this wonderful job. And I'm sure that the code drills will go up to heights in the coming months, coming years. And the next is the problem setting team. They work really very hard, very, very hard, because you know the situation now. People are working from different geographical locations. Even now they have joined. And we wanted to have this problem discussion because we all want you to understand, know how things work, how the problems are solved. It is a learning and experiment for you also. And there were a lot of confusions regarding the selection towards the finals, and we have freezed the selection for 2020 World Finals that is yet to happen in Moscow. And the top teams from this regional contest will definitely be given a chance in the future World Finals. There is no doubt about that. There are a lot of confusions going on. So with that, one more thing which I wanted to mention here is the sponsors who made this possible, like Huawei, IBM, JetBrains, who is the gold sponsor for entire ICPC regional contests, and finally the Amazon Web Services. All these sponsors made it possible through the funding on the right time to make sure that you all, the entire contestant community is given a positive vibe. And we will have a couple of sessions after the regional round by the sponsors to just to give you an idea on how to go ahead after the contest, and to think from the career point of view. So I'm sure that you are all eagerly waiting for the results, which we are expecting to be to release it by end of tomorrow, mostly by end of tomorrow. And I know you don't have much of the time for the registration. By the time we announce the results, we will have the registration portal also open, and we will be sending you t-shirts. The registration money we collect is also for the t-shirt. It is not just for running the contest. We will send you the t-shirts to all those who are promoted to the regional round. And I'm sure that there are a lot of contestants who have emailed us asking about the t-shirts. We will definitely send. There is no doubt about that, because we want you to we want to inspire you. We want you to code more, so that in the coming years you are able to come up with laurels for the country and definitely for your career also. So with that, let me conclude, and I'm sure that you all are waiting even for the problem set discussion, which we have almost all the judges here. So before that, let me emphasize on the way in which the contest was conducted. All the judges have put a lot of efforts, especially Bala. Bala is not only the contest manager but also the chief judge. He took a lot of efforts. We had a lot of chats here and there, but at the same time, one thing I wanted to note is this contest hosted in this platform has proved that the platform itself is very strong, and that too with the help of the sponsors like IBM, AWS, Huawei, and finally the JetBrains. They made it possible. So we will have more sessions from the sponsors in the regional round as well as after the regional round for the problem discussion session. So let me conclude and hand it over to Bala to take this forward. Thank you. Thank you all.
Thank you, sir. Yeah, so I know that everyone is very eager to go forward to the problem discussion, but before that, I thought I would share some of the things that went into optimizing code drills so that we could handle the high load. I know that many people have messaged me asking like how what all goes usually into optimizing the Dutch so that it can handle high load, and that they would be very interested in knowing that. So I thought that I would make a small presentation stating the same. So we just share. Yeah, so first of all, before starting, as I said, this was the largest regional conducted, and there are like lots of team, around 4,300 teams. And so at the start itself, we expected a really high load, and it did not disappoint. The load was really high, even more than what we planned. But luckily, due to all the planning that I and Deepa did, we were able to handle even the higher load than expected during the contest. So for some stats, there were around 84,000 total submission. So the submission shown on the contest page just shows the full submission, but the judge, of course, has to evaluate all the sample and custom submission too. So including all that, there were around 84,000 submissions, which is a lot. We were getting, at certain points, we were getting constantly at 100 per second, 500 per second. At one point, we thought it was going to around 250 and so on. So that was the high amount of load that we were expecting. And so let me just go into how the architecture of the platform is. And the reason I'm telling all the details is that most of you would be participants in competitive coding, and most probably in future you will be a software engineer working in companies. And these are all the things that go into making a high scale platform. So hopefully you will find it useful. So here's the system architecture of CodeRids, and it's like a pretty standard one. This is what most high scale or high load sites have it. So first, there is always a proxy or a load balancer, which is what you connect to when any API call is made to CodeRids, and it handles or it passes on all the requests or anything to the server, and whatever response comes. So everything goes via load balancer, and then there are the servers themselves which perform all the logic. It has the actual logic, and they of course store the data in a DB. We use MySQL, and for optimization and load handling, we also use a cache. We use Redis. Now the important part is the worker queue. So when you hear of submission queue, this is what happens. Whenever a submission comes, the server first divides this into small tasks. So running a test case could be a task. So there might be 10 test cases for a particular problem submission. So all these are queued in the request queue, and there are a bunch of worker nodes. and these worker nodes would then execute that request, and whatever the response is, say maybe there's a runtime error, or maybe the time limit or memory limit exceeded, or it did complete successfully and produce an output. All these, whatever the result is, it puts it back to the response queue. And then finally, like the server again looks at the response and calculates the overall. So say all the test cases are passing, then it will mark the submission as accepted and calculate the time or memory limit taken. So yeah, I hope that that was pretty straightforward logic generally. But the interesting thing, so all these are like, if you think about it, pretty straightforward so what, but it becomes very interesting when you have to do this at high load, when there are thousands of requests pending, or when at the start of the contest, when there are 50, 60,000 people, 50, 60,000 pages all being loaded simultaneously. So you have to be very careful about how you do, or what are the code, how, which part you cache, which part you don't, and so on. So before going that, I would just go into one particular detail of how exactly a submission is processed. So a submission is processed in Codils by like, it's first broken up into a bunch of tasks. One task is to just compile it. So the compile just runs the compile command. So all of these are done in Docker, so that we can support any language or anything easily. So first the compilation is done, and so how this works is, again, we put the compile task in the request queue, and the worker node compiles it and puts the result in the response queue. And once the server comes in or the compilation was successful, it will now fan out all the test cases. So the test cases itself has two parts. One just runs the program against the test input and produces the test output. The other is the checker or verifier for that, which verifies whether the output produced by the user program matches with the one that is the expected test case, which is uploaded by the setter. And finally, when all of them are done, we finally compute the result itself. So this is our typical, so it's like a common thing across all online judges. This is our typical program is evaluated. Now, before talking about the exact optimization, so I will give a high level overview. So the types of optimization that is required for handling high load. First is code level optimization. So you might have that we should not make a lot of DB calls, and we should not make a lot of fan out requests, and so on. So that is the first level of optimization, code itself. And the second level would be to tune the parameters of a single instance. So the goal behind that is, if there is a single instance of server running, what is the maximum QPS that can be supported by that server? And what are all the bottlenecks for that? And we have to carefully tune and make sure that so as we add more resource, the number of QPS supported by one server also increases. And finally, even one server is generally not enough if the load goes very high, like we expected for the preliminary round. So for that, we now need to handle multiple servers. Now, adding multiple servers comes with its own set of challenges. It's not just as easy as just adding more instances running. So I will talk about all the three levels of optimization. So in scaling code, like I said, the main aim is to, I think this will be the most familiar to competitive coders, because we, at some point of the other, we have some solution which is timing out and we try to optimize it. And it's very similar to that. So the types of thing that is done. So first is pagination. This is to keep the request response bounded. So one example is the teams page in the contest. So earlier we did not paginate it. So every time you call it, all the teams were fetched and written. Now that won't work if we have 3,000, like 4,500 teams. So what we did was we paginated it. So only one page was fetched at a time. So that puts a bound. We know that at any point of time, more than 100 teams can't be displayed. And that like makes things very easy. And the second is fan out call. So as you can imagine, the scoreboard is the most complex part apart from the judging queue itself. It has to calculate the score, and it has to populate the name of the team and what is the penalty, and add links to that. And it has to do it in a live contest very frequently, so that there's a reasonable liveness. So we can't say that we are updating every half an hour. It has to be like every 30 seconds, every 1 minute. So scoreboard was a very critical and complex part of that. The one thing in scoreboard we observed was that there are a lot of fan out calls. So just to display the scoreboard, we fetched all the ranks, and then we have to fetch all the team names and the link to their team, as well as all the problem submission links and all. So that's one of the first thing we optimize. So how we optimize these things is we cache the end result itself. So say every 30 seconds, we can compute the scoreboard and also fetch all the things that is required to display them and then just cache it. And whenever a request comes, we just fetch it from the cache instead of calculating it again and this. And this makes everything blazing fast because you don't need to compute at all. The only task that is done in that request is just fetch from the cache and return. So that's what it. And the other thing is that we always look to cache in front end also. So one example of this is the editor preference. So you can, if you have used the site, you know that we can select what is the editor background color, key bindings, etc. Now, earlier we fetched it on each page load, but that's not really required. So we started caching it in the front end and avoiding the API call to backend. And the final thing that really helped was optimizing DB queries. So there are a lot of queries to the database, and we looked at each query and made sure that so there's this command called explain, which shows which indexes are used, and we made sure that all the proper indexes are being used, and if not, we added the index. So this was the thing. Now I will also give one particular example. Even after doing all this, what we observed was that while it was handling load properly, a particular submission was taking a long time. So for example, even apples and bananas, which is the simplest problem, even the sample submission for that used to take around 5 seconds without any load when there was no load. So that was like simply not okay for us. So what we did was we first like tracked down what all part were causing this delay. So one thing that is always unavoidable is the round trip time from the browser to the server and back. Now excluding that, everything was in our hand. So what we observed, first thing we changed there was that how it used to work earlier was there used to submission used to be made, and then every 2 seconds we used to fetch the status of the submission, and whenever it was completed, we used to display it. So there was a 2 second gap there. So even though the server was finishing fast, the it was not displaying in the front end for 2 more seconds because that's how long it took to fetch it. So that was the first thing we optimized. Instead of fetching every 2 seconds, we did a standard technique called long polling, where we just browser just opens a connection to the server and keeps it open. And whenever we have completed the submission evaluation, it just sends back the result. So as soon as it's completed, it sends back. So there is no 2 second delay. And we also did a bunch of others, all the optimization that I mentioned here, caching the problem, test cases, etc., etc. But even after that, we found that it was still taking around maybe like 2 seconds. Even though like 2 seconds would have been good enough, we wanted still faster. So we dug into really into how where exactly the time was taking. So the reason was that to see a simple apple and banana submission would take just 80 milliseconds of actual execution time. And even excluding the RTT, where exactly did the 2 second come from? So if you recall the how exactly a submission is evaluated, we notice that so each submission has all these tasks, right? And all this for every task, it has to be added to the queue, and the worker will evaluate it and add to the response. When we trace where exactly each submission is taking time, we notice that the actual most of the time was spending in adding to the queue. So the queue is a distributed queue, since we can't. It has to guarantee that if it sends an acknowledgement, it will deliver the task. Otherwise, we will have some lost submission. So now, by the nature of distributed queue, it is high latency. So we observed that each time we added to a queue, there was a latency of 300 milliseconds. Now, if you see for a simple sample test case, there is only one test case, but there are three tasks for that: compile, running the test case one, and checking the test case two. And each task we were adding to the queue 2 times. So that means that each task was taking 600 milliseconds just being waiting for acknowledgement from queue. And there are three tasks, so 1.8 second there itself we are spending. And so what we did was that, I think it would be pretty obvious by now, was combine all these tasks. So the first thing we did was combine the run and check, so that the same worker node will process both running of the task and checking of that. That also had some unintended effect of good effect of caching all the result in that worker node itself. And this also reduced the amount of time each test case wait for the queue. So now for a simple apple and banana, we only have two tasks, which is compile and run and check test. So that reduced it to around easily to around 1.5 seconds. But of course, like any good coder, we felt that even that was not enough. Could we do better? So especially for larger test cases, right? So if there are multiple test cases, then what? So we reduced even that by doing some batching of across test cases itself. So we might have like bundle a group of test cases and evaluate all of them in a single worker node, thus again reducing the amount of time spent waiting for the queue. This was especially useful for our interview problems because in interview problem, we don't have the concept of test case per number of test case per file, rather it's only one test case per file. And to cover all the edge cases, we had like 30, 40 test cases per problem. So all this batching and all really showed the effect here. And also for competitive part, especially at high load, this really optimize the amount of time a particular user had to wait. And but even after that, we felt that it took around 1.2 seconds or so, and even that we were not really satisfied. So we again tried to bundle more, and at the end, so for a simple submission, this was the case for any sample submission, and for the first one or two problem in the regional, all the things were bundled into a single task. Like it will compile, it will run the test case one and run the test case two, and compute the result and do that. So all of this then made sure that we were only adding to the queue once. So the entire batch is a single task, so it's being added to the queue once, and worker will process all the tasks and add it back to the. Now you might ask, like, why not do this for everything? Then that would actually be like counterproductive, because adding a lot of test case to a single worker node will cause that to run for a long time. So especially consider, say, languages which have a time limit multiplier, Java or Python. So those take a long time to process one test case. So if everything is run one after the another on a single worker node, then it will take a lot of time. So we, after some tuning, we decided that 2 per batch was the optimal one. So that's what we did. And after doing all this optimization, we found that simple submission took less than 1 second, which is what we wanted. And finally, like, we were happy with the result. I think if everything was fine, the internet connection was well, and all the caches were loaded properly, then it took around 800 milliseconds for a simple submission from end to end, like from the moment a user pressed submit to the moment they saw the result. So I just like this, I went into detail just to give an example of how one particular area we looked into detail and optimized. Like this, we did for a bunch of areas, scoreboard, teams, and everything. And one more optimization that was really useful, and it was actually suggested by a lot of people and our judges, was to skip submissions if some earlier test cases fail. So if in a batch, one of the earlier test case failed, we just started skipping it, and it really helped a lot, especially in TLE. So if you think that TLE was the hardest cases generally, because it took up all the time that was allotted to the worker. And if you have a large submission in Python and with a large time limit problem, they would take up like 10, 15 seconds of the worker. And in that time, that worker node could not do any other work. So adding this skip really improved the performance for large test cases. So that was for the level 1 coding. I will quickly also go through the other two instances. I won't go into full detail. For a single instance, the main thing was finding a bottleneck. So usually what happened is you would expect just increasing the CPU or increasing something would increase the QPS that is handled by that server. Unfortunately, that's not the case. And the reason for this is called bottleneck resources. So there are a bunch of resources, all of which should be at the optimal level for the QPS to be high. So by resources, what I mean, the resources, for example, in our case, are the CPU, memory, server threads, and DB connections, and the cache connections. So all of these have to be properly tuned. So for example, we can't just say that have 1,000 of each also. So for example, if you say have 1,000 server thread and we have only 4 CPU cores, that would mean that majority of time is just spent in context switching between the threads. So we have to be careful about the exact number of threads. It can't be too low. If it is too low, then that means the CPU is not being used optimally. So for each of these resources, we performed careful load tests and tuned the exact optimal number of each of these resources for that particular instance. So once we done that, a single instance was fully optimized. But yeah, even then, like I told, a single instance can't handle a large amount of load, and also it won't be resilient. Say one single instance goes down, then what will happen? The entire site will go down till we restart it again. So for all of this, the next part comes in where we just add multiple instances. Now, ideally, this should be easy just adding, but in practical, there's a lot of issues around this. The main thing around this is concurrency issue. So say, for example, if you recall the how an submission is evaluated, there are multiple tasks for the same submission. Now, what happens if the result for these tasks goes to different instances? So earlier, when we just naively added instances, there was some issue where that there was a race condition between updating the submission result by two different server instances. So all these issues had to be handled for us to support multiple instances. And of course, like the how we handle that particular error is using transactions, making sure that we open the transaction with DB and only then updated and then close, so that if there was a conflicting update at that time, that was denied. And this, especially scaling multiple instances, especially critical for worker nodes. So the ideal way this would work is called linear scaling. So it would just mean that, say, you could support 1,000 QPS for a server, and if you add one more server, then it should ideally support 2,000 QPS. Now, due to other resources or other bottlenecks, this might not always be possible. So that was what we were doing at the end to make sure that if by just adding a new instance, we would be able to handle more load. So this, especially for worker nodes, we wanted to ensure that if the queue started building up, then all we had to do was to increase the number of nodes and it should be able to handle it. So there was a lot of work that went into doing that, because then DB usually became the bottleneck, because DB instances, we just wanted to keep one. We did not want to shard or anything, because that usually becomes too complicated. Instead, like, we managed to do everything using just one instance by carefully ensuring that we don't write to DB often. So yeah, I think like these are all the things that go, but we didn't just do this in a vacuum. So we always had load tests. So what load test does is that we just have a bunch of users, and all of them virtual user, all of them bombarding the server with the expected QPS that we had. So we already know what would be the expected number of teams, and we estimated the number of users that would be there. And we had to ensure that that particular user and that particular number of QPS would be handled. So we built load test for that. And using that, we did all the optimizations that we spoke earlier. So there are like a bunch of optimization which are still pending, but those were not really needed because it was still handling the load. So this was our main thing for testing whether optimization was needed or not. And as you can see, the first time we got this load result was the time when we were really confident that we would handle the load. It was, I think, 40 or 50th time we were running this load test, and it was during that time only, like finally when everything fell into place, everything was optimized, and there were 0 request failures if you see, and the average response time was below 500 milliseconds for 5,000 users. So yeah, like that was so these are all the things that usually go into it. Of course, like these are not in a vacuum. While I and Deepa were working on the code and everything, there were a lot of inputs from other people. I would like to thank the whole of our judging team who always gave all this input, all this micro optimization, especially Vichitra, Ashwin, Kevin, etc. All of them helped a lot in making sure that the worker were secure, it was handling good load. I think like, yeah, that's all that I had for the optimization part. Next, of course, like you would be, I'm sure you would be eagerly waiting for the problem discussion itself. Vichitra will take over and drive it.
Yeah, okay. So yeah, we will start with the problem discussion. So first of all, yeah, I would like to give credits to all the people who are involved in the contest. So first of all, Balaji for the chief judge of the contest. And yeah.
So contest admin was Vijit. Then problem setting coordinators, Ashish Gupta, Kevin, and Vaibhav. Then setters for the prelims was like Ajinkya, Vijit, Divyansh, and Udit. So for testing, we had like Shijit, Ashish, Kevin. Yeah, there are a lot of people. Nevin, Saumaditya, Shashwant, Suneet. Yeah, like I'm not wasting time like reading all of the names, but then yeah, like you can see them here. It's there also on the Code First blog. Then for platform, like would like to thank Deepa and Balaji. Then like Mahesh Chaitanya for our CD of Amritapuri contest. Yeah, so these are the 6 problems.
Hey, Ashwin.
Hey, hi. Yeah, which is I can share. You can take over from here. The screen is visible.
Yeah, sure. Yeah, so for the prelims, we had 6 problems, pretty much balanced set. First problem being the cakewalk, followed by simple, then one easy, then one easy medium, then one medium hard. So yeah, as we expected, the number of submissions were also, in the same order, and the set went pretty much how we expected. So, Ashwin, can you go to next slide? Yeah, so problem 1, we had 3,248 accepted submissions. Those are the number of different teams who solved it. It was authored by Ajinkya, and yeah, of course, it's a cakewalk. And I think Varad would be explaining the problem. Varad, are you there?
Yeah, hi. I'm audible, right?
Yeah.
So as already discussed, this was a cakewalk problem. I'll quickly share the problem statement. So in this, basically we had like n people standing in a row, and it was given that the ith person looks at the I plus 1th person. Basically, the first person looks at the second looks at the third, and so on. The problem was that we knew the marital status of some people, and some of the people had unknown status. We had to, so regardless of what these unknown people have, like regardless they're married or unmarried, we had to say if there's at least one married person looking at an unmarried person. Okay, so I guess this was quite straightforward, and we just had to basically the problem breaks down to, I mean, we have to firstly ignore all the question marks. We just have to do nothing there, and we just have to check if there is a married person after an unmarried person in the, sorry, we just have to check that if there's an unmarried person after a married person in the string. So yeah, I guess that was the main thing, that we had to just ignore all the question marks, regardless of what the question marks take. If there is at least one unmarried person after the married person, the answer will always be yes. And I guess it is quite straightforward to even prove that. And yeah, I guess that was it. And also there were actually many questions asked to us during the contest, like if the string is question mark, there always we could have assigned mu and said the answer is yes. But actually the problem was, for any possible combination, there should be at least one mu pair, right? So if there were 2 question marks in a row, we can always just replace it with uu or say which is invalid, right? So for every such combination, we needed at least one mu pair. So yeah, that was it. And the time complexity, again, this can be implemented in O of n using a simple flag variable, or the many implementations actually. And obviously the constraints were very relaxed, so even O of n square implementations were allowed. And yeah, I guess that is it for this problem.
Thanks, Varad. Ashwin, can you go to the next slide? Yeah, the second easiest problem of the set was express the number, and 1,918 teams solved this problem. This problem was prepared by me, and Ashwin would be taking for the explanation.
Yeah, so the problem was given a number and we had to represent it as sum of k numbers. And there's this condition with the k numbers was that the first number could be less than or equal to a given x, and or the first number could be a odd power of 2, and remaining numbers in the k numbers should be odd power of 2. So to start with the obvious, x can be 0, and the not possible condition would be if x is 0 and n is odd, we would never be able to make 1 required for the number to be odd, and so it would be a not possible condition. In the otherwise, what we would do is take the binary representation of the number n, and there would be each bit would be a 2's power, and if it's 2 raised to k and it's greater than x, then we skip it. Otherwise, we subtract it from the number. And if it's 2 raised to k is greater than x, we increase the answer by 1. And for even powers, we can know that like even powers of like 2 can be represented as sum of 2 odd powers. If k is even, we can represent it as 2 raised to k minus 1 plus 2 raised to k minus 1. So what we can do here is again subtract 2 raised to k minus 1 from the n. So every time we find a power of 2 that is like less than x, we keep subtracting it from we keep subtracting the 2's power till like the number becomes n becomes like less than or equal to x. So once the number becomes less than or equal to x, then whatever is left over can be taken as the first number, and we can say that okay, like the first number is the leftover, and the remaining number of 2's power that we eliminated is part of the answer, and we obviously include the first number, that is the a1, and like the total number of numbers that we found out would be the minimum or the best way to represent the n as sum of k numbers. So in this question we were supposed to minimize k, so this is one of the strategies.
Okay. Okay, thanks, Ashwin. And yeah, before going to the next problem, I would like to, put a fact. This year, like generally the previous year, graduates help in setting and testing for the round, but because this year it was delayed and 2021 grades are, participating, so it was very hard to get testers and setters. But yeah, somehow we got, people, and yeah, that was a great effort by all those guys. That was special shout out to all those people. Okay, and now I think we would be moving to P5 first. Ashwin, can you go to P5? Yeah, so in the P5 we had number of accepted teams who got ACs 56, and problem was authored by Divyansh, and yeah, even Divyansh would be taking to explain the problem. Divyansh, you there?
Yeah, am I audible?
Yeah.
Yeah, this problem consists of lots of strings. So it's lots of strings. We are given a set of strings, and we need to we can take any string and put it in order. So what we need to do after putting each string back to back, we need to find the largest good subsequence. So what is a good subsequence? Subsequence is the one in which all the characters are in increasing order. So for this question, there was a twist that Q was really large. The initial problem we didn't expect, while problem setting this, Q was taken to be small. Then Ajinkya Para given the idea that Q can be large and we can solve this even then. So yeah, let us discuss the solution now. First of all, you will see that for an increasing order, we can at most switch the characters up to 25 times, like A, B, C, D, and up to Z. We can't do it more than that. So instead, so string is going to be changed only 25 times. Other than that, there will be a single string which will have a repeated set of characters, which will be placed like Q minus 25 times, or maybe less than that. It depends upon the number of increasing, number of characters we have increasing order. So yeah, this was the twist in this question. So yeah, next slide. So L plus R be the number of words which are going to be in increasing order. Then what we can do is we can just find out the max occurrence, that is the character which has the maximum occurrence in a particular string, and that let it be max occurrence of X. Now for finding the real answer, what we need to do, we need to find a longest subsequence which we can form using C word with characters from 0 to some I or J, from A to some character. And after that, we will repeat the longest maximum occurring character, and then we will take other characters R times, which will be from the maximum occurring character and up to the Z thing. Yeah, next slide, please. So the longest subsequence, which is taken C times, longest sequence which can be formed using C different strings. We start from I and end at J, can be computed using DP. The formula is pretty standard, so you can see it on the screen. like it's max of over k, longest c minus 1, I, k, and plus longest of 1, k, comma, j. So we can find out that. So overall complexity will be size of sum of length of all the strings into size of alphabet, which is 26 square plus 26 raised to the power 4. Yeah, that's it. Other than that, there were also few solutions which I have seen. They can, like, this problem can be, I will not say it can be easily, but somehow it can be like make into a standard graph solution. I've seen the solution, but I don't know how it can be solved. Yeah, so some solution we have seen in that way too. Yeah, that's it.
Cool. Sven, can you come back to P3? Yeah, before P3, I guess. Yeah, so during the round, what we were doing, so yeah, some fun during the round. We were just trolling the cheaters, joining some Telegram groups, and we just put some messages, and people were asking us for the solutions, and yeah, that was pretty much fun. Sven, next slide. So P3 was the third easiest problem of the set, being an easy, and we got around 1069 teams who solved it. Again, this problem was prepared by Ajinkya, proposed by Ajinkya. And Ajinkya would, one more thing around this problem. So like until the last day, we had some version of this problem, but then Kevin started testing it and he found out that the greedy solution is wrong. So the good that we found out before the round. So we had to, change the cost function for the merging from max x1, x2 to x1 plus x2. So that was a twist. We were not able to prove it. And later we also found a counter case where the greedy solution fails. But yeah, we were able to catch it before the round and we fixed the data. And I think now Ajinkya can take up the problem for explanation.
Yeah. Hi. Am I audible?
Yeah.
So yeah, before we go into the solution, let me first explain the problem very briefly. So in this problem, we were given n arrays, and what we had to do was we had to form a single sorted array out of them. And we were allowed to perform two different operations. The first one was to break any of the arrays at any given point, such that we now have two non-empty different arrays. And the second operation was to merge any of the two available arrays. And we merge it in such a way that the elements of the two arrays can interleave among themselves, but the individual order of the arrays, of the elements in the arrays, cannot change. And each of these operations had a cost function associated with it. So yeah, the basic aim was to finally get a single sorted array. And it's easy to see that we can always form a single sorted array using these two operations. And one of the most obvious ways is to just keep on breaking the array until we have single elements, and then just start merging them one by one. But anyway, the problem wanted us to solve this with the minimum cost. So yeah, to solve that problem, we required a lot of simple, but many small greedy insights. So yeah, let's just look at them one by one. So the first observation here was that we could do all the splits, like all the breaks before all the merges. And doing this would not add any additional cost to our overall process. So yeah, it's quite easy to see that doing all the splits first and then all the merges later does not affect the total cost. And this can be more seen in a better way once we look at how we are going to merge all the arrays. So yeah, can we go to the next slide? Yeah, so once we have decided that we will do all the splits before the merges, let's look at how we are going to break the arrays. So how are we going to split them? So one of the obvious things is that we will anyway need to break the array at every point whenever an AI is greater than its next element, that is AI plus 1. So whenever this happens, we will have to break it. Otherwise, we won't be able to form a single array because the second operation won't help us do this. So this break is always necessary. And it can be seen also easy to notice that no additional breaks are necessary. Again, this is more obvious when we look at how we are going to merge the arrays. But yeah, the main observation was that we are going to break at every point whenever the next element is smaller than a given element. And yeah, once we have decided that where we are going to split the array, the next point is how we are going to split it, because the break function also had an associated cost with it. So the cost for the break function was the minimum of the two broken parts of the array. So to do that, again, we can do this greedily. So suppose we had the array A and we decided from our previous observation that we are going to break it into n different parts, like A1, A2, and up to AN. So we can always try to cut the leftmost or the rightmost AI, whichever is smaller. And we can see that by doing this, at the end, whatever remains will be the maximum AI. And so the cost for this overall splitting would be the size of the array A minus the maximum AI in that array. And again, it is easy to see that this is the best possible cost, because yeah, we cannot really get anything better than this. So yeah, let's move on to the next part. Yeah, so we are done with all the splits. So the next part is to actually merge those arrays. And yeah, by looking at how we are going to merge this, it will also be clearer as to why some of the assumptions that we made previously make sense now. So when we are going to merge the arrays, we have already broken down the arrays into say increasing arrays now. So we can just merge them one by one so that we finally have one single sorted array. And how are we going to do this? The cost function for this was the sum of the arrays that are going to be merged. And yeah, as Vichitra said earlier, this cost function was initially something else at the beginning, but we decided to go with this because yeah, this is quite a standard cost function actually, and we are going to see how in some time. But yeah, let's try to see why this works. So what we are going to do is we are going to choose the two smallest arrays available at any time and merge them. And we keep on doing this until we finally have a single sorted array. So why does this work? So yeah, if we are going to merge some small array AI CI times, then it is going to contribute CI times the size of AI to the total cost. And if we imagine this whole process to be like a tree, then all the AIs, the split arrays, are leaves in this merging tree. And CI will be the depth of those leaves in this tree. So what we want to do is we want to rearrange the leaves in whichever way we want, such that the total cost is minimized. And to do that, we would always want the smallest AIs to be together and in the deepest leaves of this tree, so that if whatever CI is used, so the maximum CI is used for the smallest AI. So that is what we would want to do. So at every point, we would try to keep the smaller AIs as deep as possible in this merging tree. So yeah, can we move on to the next slide, please? So yeah, if we look at this, so what we want is we always want the shortest arrays to be as deep as possible. And with repeating this argument again and again, we can see why this also works. And as I said before, this is quite a standard problem. This proof basically also proves why the Huffman coding works. So yeah, this was basically the expected solution. So at every point, we try to find the two smallest arrays that we have and then merge them. And how do we implement it? We can use a priority queue for that. So just choose two of the smallest arrays from priority queue and then merge them and then again insert it back. So the overall complexity for this part would be S log S, as stated here, where S is the sum of lengths of all the arrays. So yeah, basically that was it. So combining all of this, we finally get the optimal answer that we want.
Yeah. Thanks, Ajinkya. So again, some more trolls. Can you go to next slide? Yeah, problem 4 was it was easy, medium, around as we estimated. But I feel like this problem was even little easy than the P3, but as we expected that there won't be many submissions on this, and yeah, there were less submissions than P3 on this problem. The teams who solved it 255, I authored the problem and Ajinkya prepared it, and I would be presenting the solution. Ashwin, can you go to next slide? Yeah, so this problem, like we are given a graph and which is not necessarily connected. And what we want to do is like we want to find a connected subgraph which contains all the nodes and it's also bipartite. And additional condition was like the weight of the whole graph should be minimum. Now, like looking at this part that it should be connected bipartite subgraph, again, always tree comes to my mind. Like tree is a simplest bipartite graph. So that was the only observation this problem needed to solve. So yeah, so once we notice that a tree can be a valid answer, then the part was to minimize the weight. So that can be minimized by picking up the MST of the graph. Like we always use the existing edges, then we add some more edges. The cost was absolute value of AU minus AV. But yeah, what can we do is like we can yeah, this next slide. Yeah, so we can sort all the nodes by AI values and then picking up on only the consecutive nodes and put one edge between them, because like we know that we can form a tree within n-1 edges. So like we already have some edges, and again by sorting them and picking only consecutive ones, we get n-1 edges. And Hodge cost is like AU comma AV. Considering AU comma AV, the absolute value is minimum if they are consecutive. Because if we take any other pair, let's say some Z, then V to Z and Z to V, that would be even more cost. So this was again one more insight to start with the greedy solution. Now, like we can consider only these edges and sort them with the cost, and then we can start picking the ones with the smaller cost. And the solution can be implemented either by forming the MST, or we can also do union merging. So both of the solutions take n plus m log n time. And yeah, and like we thought like there might be more possible solutions to this problem. So we had put limit like the outputted graph can have up to 2n edges. Like we thought that there might be more subgraphs which are bipartite, and if someone thinks, then that should be okay to accept. So in next slide, P6. Yeah, so for this problem, P6 tree maximum, before the problem, like we got a lot help from Kevin. So Kevin was the one of the person who was the problem coordinator, and he helped throughout the process, and like he helped in each problem, finding out if there are any mistakes, and he had put written some formal proofs of each problem, each greedy solution. And for this problem, tree maximum, he wrote a paper having 10 pages, and the proof is very long. So glad that we had Kevin in team, and he helped a lot to formalize the things. And we were very sure that now all the solutions are correct, and we were quite confident that there won't be issues after the round. And about this particular problem, this problem is prepared by Udit, and this got 0 submissions, which we did not expect. We were thinking like there would be around less than 5 submissions accepted, but we got 0. And before going to the solution, I would like to thank the whole IUI gang who joined us to help for the setting and testing, because like again, as I told in the start that recent graduates were not here to help us because they are participating. So we were not able to find enough people to test and set. So we got whole IUI people. we took the future ICPC participants for the management of the round. So a huge thanks to all the IUI gang. And now I think Udit can. And one more thing, like we had a simple version of this problem which was proposed, which had, I think, only one condition. But later Udit came up with like, let's add one more factor that we can select at most k nodes. And yeah, many testers said that this is very common idea, and like both of the problems separately exist somewhere. And we thought that, yeah, if everyone is complaining about it, it's better to use in online round. But sadly, it was not that easy. So now I would hand over to Udit to explain the solution. Udit, you there?
Yes. Am I audible?
Yeah.
Yes. So the problem was that you're given a tree. You can select at max k nodes from the tree such that the pairwise distance between any two nodes is at least h. And you have to maximize the values of the values at the node, sum of values at the nodes. So the first natural thing to do would be to root the tree, and then we'll do a DP on the tree. So we define a DP IHK, which is consider the subtree of the node I, and we'll be picking at max k nodes from the tree, and the closest node from the node I should be at least at a distance of h. So in this, we can do a O of h square times k square times number of children merge. I'll show the code in the next slide. So this is basically O of n to the power 5, which is very slow. Next slide. It can be improved a little bit. So we can do several improvements in the inequalities to get, instead of O of n to the power 5, we can do O of n to the power 4. Can you show the next slide? So this was the brute n to the power 5 code. This is, we are doing just a DFS and doing the standard DP on tree merging. So this is the main part, the max DP, this thing. First, we are iterating over the current minimum height, minimum depth, then the current number of nodes, then the next, the height, the depth will be taken from the new children subtree, and then the number of nodes will be taken there. So it will be the current. I mean, you can see the recurrence. If you spend some time to think about it, then you'll get it. So here, this code is n to the power 5, but we can do a few improvements to this. First of all, we can observe that we don't need to iterate over this IV variable. It's enough to just consider two values of it. One is the case where IV will be the new minimum, and one is the case where the current minimum will stay the minimum depth. So another improvement we can do is, instead of iterating from 0 to k, we can iterate from 0 to k, comma subtree size, because we can't take more than subtree number of nodes. So with these observations, I think you can get n to the power 4 easily, or maybe even n cube. So next slide. Yeah. So also, apart from n cube and n power 4, if you do some particular sets of inequalities, you also get nhk times min of h comma k. I think Kevin got this solution first, so this is in reference to that. This slide is. So first, we have two observations now. First observation is the value of h into k is not that large. So this is a little intuitive. So if all the nodes are at h depth apart, obviously you can't take a lot of nodes. So we'll be showing that you can only take at max 2n by h nodes. And the worst cases where there's a center and there's chains of length h by 2. So all the n nodes you will be able to take. So 2n by h nodes you can take. So we can assume that hk is of the order n, and using this we can also see that min of h comma k is of the order root n. So this O of nhk, min h comma k, can become O of n to the power 2.5. So this still doesn't completely pass, so we'll have to think of better solution. Next. The proof of the first observation is that consider any node we are taking and mark all the h by 2, all the nodes which are at a distance strictly less than h by 2 to it. So you can observe that no node will be marked twice, and at each step we'll be marking at least h by 2 nodes, a seal of h by 2 nodes. So the total number of nodes taken is 2n by h. There's one case where we won't be marking h by 2 nodes because the distance is already less than, the total number of nodes is already less than h by 2. So in that case, we only mark one node. So it's max of 1 comma 2n by h. Yeah, next. So now the next observation is that in the first recurrence we were doing min of k comma subtree size. Instead of that, we can do min of k comma subtree size by h. Min of k comma 2 into subtree size by h. So because of the observation 1, we can see that this is n of number of nodes. This is the max number of nodes we can take in that subtree. So just iterating from 0 to the new k is enough. So for the proof why these limits are now enough, we can first prove for a binary tree. So the recurrence currently takes O of h times the subtree. So the recurrence currently takes you h times subtree size of left subtree by h times subtree size of right subtree by h. So that's less than equal to subtree size L times subtree size R. So the worst case recurrence will be the time taken to compute for the left subtree plus the time taken to compute for the right subtree plus the product of the subtree sizes. So, and for generalizing this to non-binary case, we can just add an auxiliary node with zero distance and just connect the new nodes to it. So this is a standard trick where basically if you have 3 nodes, so connect the first one, then add an auxiliary node and connect second and third to it. So you can generalize this to non-binary as well. Next slide. Yeah, so this is the inductive visual proof for the case that this is at max n square. So we can inductively show that T of I is less than equal to half of I square, and then using this we can show inductively that this is this remains half of I square at all times. So another way to visualize this would be that the size of L times size of R, each pair of nodes is getting considered at max one time. So, and that point at which it will be considered will be the LCU of both the nodes. So that's another way to look at it. Next slide. So this was the new code. This KU is basically min of k comma cur by h, 2 cur by h. So, and similarly KB, and this we are doing the same DP. In this we are not iterating over h again, just considering the 2 values which we needed to consider. So this was the idea. Any questions?
Thanks, Udit, for walking through the solution. And I don't think we have any questions. And yeah, we would be publishing the editorials in some time. I think they are almost ready, but yeah, it might take some more time. But yeah, we would be publishing all the editorials in some time, and yeah, along with the proofs, hopefully. I think yeah, the proof of last problem is pretty much ready. That again, we would publish after some time. So, Balaji, Yudhir?
Yeah, thanks for the explanation, and hope everyone learned from that. And you can always solve the problem by just going to the contest and opening the problem and solving it. We'll also publish the editorial, it will be visible there. I think that's it. Sir, anything?
Yeah, I'll just conclude. So thanks for listening. We will, as Bala said, we will share this entire editorial and video session separately in YouTube channel, and we'll be emailing this to all the contestants. So my suggestion is again to participate in more and more contests to make yourself sharp. We will be opening up opportunities in future. The future in the sense maybe in the coming months itself. So the students are asking about the 2021 ICPC regionals. We expect that by end of this year, once the situation is normal. Otherwise, we'll go online itself and keep practicing. We will also have this contest live in code drills in next couple of days once the results are published. And please prepare for the regional contest. That's on 14th of August in the evening, the same time. We will publish the rules, a few rules and regulations to be followed for the regional contest, maybe in next 1 or 2 days. So thanks and congratulations for the participation. And let me again thank all the problem setters here who worked really, really hard in spite of all the issues they face, the challenges they face, and risks they face. And once more, thanks for thanks to Bala and the Code Drills team to make this large contest happen. That is in the history of ICPC, especially from India. Thanks again. We will meet after the regional round again. Thank you.
Hi. My name is Ruslan, and I have been an intern with IBM Quantum this summer.
My name is Yeva. My research at IBM focused on studying pharmaceutically important reactions using quantum computers.
Hi, my name is Rachel Lee, and I'm currently a sophomore at Harvard studying computer science and statistics.
I'm Ramnik Tautanamo here to talk about my IBM Quantum internship experience.
Going for an internship at IBM Quantum was a no-brainer for me.
Implementing configuration management functionalities to the QTracker tool.
I knew very less about quantum computing, and I just wanted to give it a try.
At Kiskit Summer School, I learned so much about quantum computing that I hadn't known before. And it was just definitely a deep dive into theory, helping me to learn more about the complex math that underlies quantum computing and all the technical details that go into creating quantum circuits and quantum hardware.
It looked encouraging for me to apply, to work with IBM Quantum, and I am humbled to have had this opportunity.
It's a world-class science, and it's done by world-class groups.
This internship has definitely changed my future plans.
I realized that IBM offers this really great and unique space in between academia and industry for people to research. And so I'm definitely also really excited to explore that as a potential career option in the future as well.
My name is Tejas Sachdeva. I'm a recent graduate from CSU Channel Islands. Ever since I've been a kid, I've always been into technology. You know, I've kind of been the person around the house who's always fixing things, you know, playing with gadgets. So that's always been an interest of mine in technology. And when it came time for me to choose a major in college, computer science was the one. My professor actually told me about AWS Educate and how he was using the platform to teach students about cloud computing. So that was really exciting for me. And that's where my journey started with AWS Educate. It was like a cloud computing 101 course for me. None of my classes in college were really about cloud computing. So I wanted to see what it was about, how it's being used in the industry, and what are the career aspects of it. 90% of companies use some aspect of the cloud. That is huge. I can take the skills that I learned here and apply them anywhere. As soon as I got exposed to AWS Educate and I got my cloud practitioner certification, it exposed me to so many different opportunities, you know, both job-related and networking opportunities, which in the end led me to this great position at AWS Educate. I'm currently the program manager intern on the AWS Educate employer team. So my task is to mainly help students get employed. Having gone through the AWS Educate program has put me in the perfect position to help future students, because I was in their shoes not just a few months ago. Working on the Educate employer team gives me a unique lens into the program, and just in my first 6 weeks I've been able to make changes to the portal, which allows a better student experience. The opportunities with AWS are endless. If you're a college student, just dive right into AWS. It's free for students. You can take the Cloud Computing 101 track and just immerse yourself in cloud computing. Don't think twice about it, just go down this road. At the end of the day, you get to learn something new, which you can apply to other areas of your life as well.
Hello, my name is Mikhail Dvorkin. I am 2007 ICPC Gold Medalist and Kotlin enthusiast. In this short video, I will be using Kotlin to solve a sample algorithmic problem that appears sometimes on coding interviews. This problem will concern finding dictionary words inside the rectangle filled with letters. Let's go to an IntelliJ IDEA window to discuss the problem and solve it in Kotlin. First of all, I'd like to thank Solontus_ and Lalit Kundu for bringing up this problem on different websites. So the problem is, we have a rectangle filled with English letters and a set of words that we will call dictionary. And the question is, which of these words can be read in this rectangle if we are allowed to read horizontally or vertically and turn 90 degrees as many times as we want. For example, in this rectangle, we can read the word Kotlin or fun or file according to these rules. Let's hard code the rectangle with letters into our program. So this will be a row string with all these tabs and line feeds that we will deal with later. And the dictionary will be also stored as a row string that needs some processing as well. The rectangle row string has all these tabs and line feeds, so let's first remove the tabs by trimming all the indentation of the string. And now we have a single string with letters and line feeds, so let's split the string with a line feed character to receive not a single string, but a list of strings that are horizontal lines of the original rectangle. We can print the resulting variable to make sure we got our trimming right. And now for the dictionary line, let's make sure it's uppercase, just as all the letters in the original rectangle. And now with this uppercase single string, we can split it by a comma and a space to receive the list of single words of the dictionary. Actually, knowing that I want a lookup operation in this data structure to be quick, I can make this a set. Now let's actually code the method that is going to do the main work. I propose a recursive implementation over here, so let's discuss the signature of our method. For now, let it receive the coordinates of the cell that it is currently processing, but we will update this signature with some more arguments later. when we enter an instance of this recursive method, we are standing in the cell with coordinates x and y, and in general case, we want to make a recursive call into each of the 4 neighbors of this cell. How do we organize the iteration over all 4 neighbors of this cell? Well, I propose a list of vectors that show the directions towards all the 4 possible neighbors. In this list, I will be using Kotlin pairs to store the direction vectors. Now, in the recursive call, I can iterate over all the possible shift vectors, and in this for loop, I will be using multiple variable assignment to introduce 2 variables, the x shift towards the new neighbor and the y shift. With these 2 variables, I can calculate the coordinates of the next cell that I will visit in the upcoming recursive call. We have the new x coordinate and the new y coordinate, but these 2 coordinates can show outside the rectangle, in which case I want to ignore this iteration of the for loop as this shift vector is useless. Also, I definitely want to know the letter that is located in these new coordinates if they indeed show inside the rectangle. So let me write the code that does these 2 things simultaneously. I could have written a simple code that makes a direct access to the 2-dimensional array by the y coordinate and then by the x coordinate. But this code raises an exception in case a y coordinate or an x coordinate goes outside the rectangle. So let me rather use nullable objects here that Kotlin handles so nicely. And instead of taking the horizontal line with such index, I will rather use the getAllNull method that will give me the horizontal line with such index or null in case this index is invalid. For this object, I want to do something only if this object is not null. So I put a question mark here, and then I apply the same method to receive the value in the certain index or null if this index is invalid. This object is the letter located in the desired coordinates or null if at any point the y coordinate or the x coordinate was pointing outside the rectangle, in which case I want to disregard the entire iteration of the for loop, which is exactly what a continue operator does. So if I have reached this point of code, then I didn't run the continue operator, and therefore my coordinates are showing to the actual cell and not outside the rectangle. So I can make a recursive call to these new coordinates. So over here I make a recursive call to the new cell that I'm sure is not a place outside the rectangle. However, this resulting code is an awful example of the infinite recursion, because each instance of my method always runs several other instances of the same method for the neighboring cells, and they do the same recursively, and so on and so on and so on. So we need to stop our recursion at some condition. In order to do this, let's change the signature of our method so that it receives the word that has been already read during the previous recursive calls. With this word, we can stop the recursion if this word is not a prefix of any word in the dictionary. We need to pre-calculate before the recursion the set of all the prefixes of all the words in the dictionary. Let's take our dictionary, and I could have used the map method to receive the list of lists of all the prefixes of the words in the dictionary. But what I actually need is the concatenation of such lists. So instead of the map method, I will use the flat map method that will do exactly the thing. inside this flat map method, I want to receive the collection of all the prefixes of the given word. So let me introduce the word variable that I will be working with. And here I need to construct a collection with its prefixes. It will be a list, and the length of this list will be the length of my word plus 1. And for each index, I want to generate the prefix of my word with the corresponding length. So from my word, I take the corresponding number of letters. And once again, since I want the lookup operation to work quickly, this overall collection should be rather taken as a set, not a list. Now let's get back to the recursive method. In case the already read word is not a prefix of any valid word in the dictionary, just disregard the entire recursive call. And if the current read word is exactly a word from the dictionary, let's print it to the answer. And the recursive call to the neighboring cell should also pass the correct argument to the method. So it will be the already read word plus the letter that we have seen in the new cell. Now we are ready to make a call of the recursive method for each cell of the rectangle. In order to do this, we iterate over all the possible values of y coordinate, and instead of writing the specific lower and upper bounds, I'd rather write the indices of the rectangle, because this is exactly the values for y that I want to iterate over, and I will not make a mistake by +1 or -1 in such code. Now, for the x coordinate, let me also write some code that will be safe from +1 or -1 mistakes. So these are the indices of the horizontal line, for example, number 0. And for each y and for each x, I make a call to the method search with these two coordinates, and the word that I start with is the word consisting of a single letter in these coordinates, passed as a string. These for loops will run the recursive search from each starting point, and these recursive searches will print all the found words to the output. So let's run this code to find all the words in our rectangle. And we see that our rectangle contains all the words from the dictionary except for the word null. The basic problem is solved, but the important exercise yet to be done is to forbid ourselves from coming to the same cell several times, because it's a very natural thing to disallow, and our code still allows such behavior. So I leave it as an exercise for you, or probably we will do this in some other later video. Thank you for watching this video. Have fun using Kotlin and other programming languages, and good luck in your careers. Bye.